Hey everybody, we're going to talk about Anova or analysis of variance today, and it relates to the t-test. Okay, so the t-test was great. We had some cool things, right? Even for small sample sizes, we had this robust test, and scientists really appreciated it, right? Because it worked well, and again, it expanded the options because it worked well with small sample sizes. And there are some research situations where a small sample size is kind of enforced. It's difficult sometimes to get um, a larger sample size. It's both time consuming and expensive at times to collect data, and sometimes the subjects simply aren't there. So the t-test was great, but there was a problem, right? The largest number of samples we could do was two samples, right? We have independent samples, matched pairs, but we don't have a way to take on a variable that was a category variable that had more than two levels, right? So we had a four-level variable like year in school, freshman, sophomore, junior, senior. That's a four-level category variable, and we don't have a t-test for it. So there are a couple of options, right? We could, sorry, let me move forward there. We could, there are four groups, right? Freshman, sophomore, junior, senior. We could do all four choose two equals six pairwise t-tests. And you're like, well, six t-tests, it might take a while, but we've got R, that's not impossible. The problem is that every single one of those six tests has a 0.05 error rate, type 1 error rate. So it's not quite that we're up to 30% of a type 1 error, but we have increased the type 1 error pretty massively to the point where, you know, you don't want an error rate of 20 or 25%. And again, if it's more than four levels in the category variable, that's more tests. And then we're at five choose two or six choose two or seven choose two. And we've done so many t-tests with so many of these 0.05s piling up that we have almost no chance of a correct conclusion. So just running a bunch of t-tests on all the pairs doesn't work. But if you remember from the Lady Tasting Tea, Ron Fisher was the gentleman we bumped into there, and he's the one who took up the challenge. He's like, look, the t-test works great. Let's create the mathematical extension that will work with three or more groups. And it turns out you can do a two-group ANOVA, and it does match what you would get with an independent samples t-test. But we generally just run the t-test in that case, right? So we generally use ANOVA for three or more groups, but it does match up with a t-test. The maximum t-test and the minimum ANOVA do match up. They don't have the same test statistic, but they'll generate the same p-values. Okay, so ANOVA analysis of variance has the same data verifications as the t-test essentially, because it has the same three baseline assumptions: normality, independence, homogeneity of the variances. But the cool thing about the F statistic, which is the thing we use in ANOVA, I assume it's for Fisher, right? His last name. But the F statistic turns out, as we add more groups, it gets even more robust than the T statistic. So the T statistic is great and robust, but the F statistic even more so. Okay, so the normality checks that we're going to do, we're going to update it slightly differently. We're going to do QQ norm on the residuals of the model. We did this for linear regression, so we're familiar with how that works. And with the homogeneity of the variances, the same, the standard deviations being equal, what are we going to do? We're going to require this, right? That the sample sizes, greatest to smallest ratio ration. Ratio of group sizes is no larger than 2 to 1. All right, and other than that, we're not going to do much except that we're going to require a sample size of at least 15, right? So if we have a three-group ANOVA, we need at least 5 subjects per group so that we have this. What's this for? Again, the ANOVA is so robust. And again, a lot of these groups are small. It's really hard to do a stem plot or a histogram or a density plot for all of the individual samples. And and run into no problems whatsoever. So again, we're going to simplify it, just have a minimum sample size, and then we'll run the QQ norm. And again, we're simplifying the data checks, although they are essentially the same assumptions as the t-test. And how is this going to go? We're going to create a model, right? And it's actually going to use LM, linear model, like we were using for regression. Okay. Why? Because we need to check the residuals of the model. Okay, so we're going to extract the residuals with residuals parentheses module. Okay, and now res are the residuals, so I can do QQ norm for the res variable, right? QQ norm of the res. And I also want to do a QQ line, right? So I'm going to see that line, and we're going to see any deviation. Also, I'm going to do a density plot just because I do. We're checking the normality assumption, the normality of the residuals. So I like to see the density plot. If the QQ plot is off, I want to see what's going on with that data. Maybe that's a little bit of morbid curiosity on my part because you don't, I suppose, really need it. But if the data are appropriate, we're going to run Anova. The Anova function is AOV. And again, we put in the model, the statistical formula. We do numeric variable first, category variable second. Okay. And again, if we do numeric tilde category, right? If we do it in that order, R understands exactly what we're trying to do. Oh, and Anova with this grouping variable, we'll use the levels of this grouping variable for our samples. And again, we're going to tell it what data frame to do this work in. And then there's an interesting thing because the Anova comes in two parts. If I reject the null, I have to conduct a post hoc test. Okay, so let's talk about what the null hypothesis is. The null hypothesis is that the means of all the samples are equal. So what's the alternative hypothesis? The alternative hypothesis is that at least one of the group means is different than the others. But it could be, let's say we have four groups, right? If we're looking at this GPA versus year data, right, we have four groups. Well, I could have two group means that are high and two that are low. I could have two in the middle, one high, one low. I could have three kind of grouped together and the fourth one high or low, right? There are lots of configurations of, at least one is different than the others. So the Anova, when we reject the null, is lacking in specificity, right? We know there's a difference somewhere, but we don't know exactly what or where. So that's why we want to do what's called post hoc test. Post hoc, I believe, is Latin for after the fact. Tukey HSD, the HSD stands for honestly significant difference. And what it does is it goes through the groups pairwise and determines where the honestly significant differences are. However, it's not pairwise t-tests. It's designed to control the overall alpha. Okay, so our alpha doesn't explode like it does with a t-test, but we do get the pairwise comparisons from the Tukey HSD test. And the call for that is just Tukey HSD. And again, if the name of the Anova is saved, if the variable name for the Anova that we saved is Anova, then we just do Tukey HSD of Anova. Okay, or we can do data, or we can do model, there's lots of different names we can give it, but whatever the name of it is, we'll save it as some variable name, and that'll be the call. So let's check out the examples that we need to do. Okay, so the first example we're going to do is perfectionism. Okay, and the first thing I want to do, what I'd like to do is set up the hypothesis. And with Anova, the hypothesis is almost easier to set up in words, but I'm going to set it up the way we normally will. And we have preference and we have sit class. Okay, so the question we asked for sit class was you show up at a classroom and almost nobody's there. So you have your choice of seats. Do you prefer to sit in the front, the middle, or the back of the classroom? All right, so we have front, middle, and back. So our null hypothesis is that those group means are all equal. Sorry, I keep trying to hit 0, colon, right? So what do we have? We have mu for the first group, which will be front, equals backslash mu for the second group, which will be middle, equals backslash mu for the third group, which is back, front, middle, back. And I need to switch this cell to Markdown. Right? So that makes sense, right? That the average for the front equals the average for the middle equals the average for the back. Okay, and perfectionism scores, we'll find those averages in a minute. But what is the alternative hypothesis? And again, at least one of the group means is different than the others. And you can say significantly different if you want to. Again, statistically significant, that's the word we use, right, is significant, right? So I'll throw that in. It is correct to say it. And now I have this issue that, oh, I put a underscore rather than a dash here. Okay. There we go. Now things are lining up better. Let me put a space in there. Okay. And so this one is easier. The alternative hypothesis is definitely easier to write out. Typing out the formula for the null hypothesis is fine. The null hypothesis is all the group means are equal. The alternative hypothesis is at least one of the group means is significantly different than the others. Okay. So what am I going to do? The next thing I want to do is a data verification. Okay, and what I'm going to do, I'm going to start with the mod is equal to LM. And what am I doing? I'm doing perf is the numeric variable tilde sit class data equals pers. And you'll notice that I've already done the read.csv for the personality data set, and it's all right there. So, and I've run it, but just to make sure, let's make sure we run it again, make sure that both the pers data set and the city data set are loaded. Okay, so it's created this model. And what do we want to do? We want to do residuals of the model. Okay. And then what? And then, well, let me get another. Okay. So you see, this is good. Let's call that res. Why? Because we're going to use the residuals to do what? To create a plot. Okay. So I'm going to do the layout matrix. See, I hope this is becoming pretty routine for you, right? Because it's comma numcol equals 2, right? And then again, LCM is usually good around 8 or 9, but we'll try things up to 11 or 12 to make it work. What am I doing? Wait, I don't. Okay, let me do it. So plot density res. Okay, so density plot on the residuals, and I'm just going to do main equals density residuals. Okay, and then I'm going to do PLT. Why? Because remember, I'm going to have two plots that I'm going to put in here. The first one I'm going to put in is a QQ plot of the residuals, right? And then I'm going to put in the QQ line of Is it the residuals or the model? I'll have to think about that for a second. And let's see if we get that to run. I am going to do this. I'm going to turn these into comments and just do the plot. And it does not like this. Okay. This is interesting because I tested this before I started creating the video. And this worked. So what if I do oh, I'm not doing a QQ plot. I'm doing QQ norm, dummy. There was the mistake. Let me get rid of this. We're going to do the res. It is a QQ plot, but the name of the function is QQ norm. Okay. Now we have the two diagnostics, and you'll see, right, that do I have heavy tails? Slightly. I have a couple here to the right where there's a few more outliers than we should have. To the right, there's something here to the left. Okay, so is there, some more outliers to the left here than there ought to be? Yes. But what do we have? We have the majority of this line. The dots are right on the line. Okay, so we just have 2 or 3 at the top, 2 or 3 at the bottom, slightly heavy tails. So this is not a problem. Okay, we are not seeing a problem here. Okay. Sorry about that slip up. What am I going to say here? First of all, I'm going to get some more space open. But I'm going to say for the data verification results, right, that we have these data are appropriate for Anova procedures. Okay. The QQ plot is extremely close to linear with only slightly heavy tails, while the density plot shows normality. Okay, so they are appropriate. The one thing we don't really have right now is the numbers, the sample sizes. Okay. That's not a huge deal, but let's do it, right? We can do that really quickly. Right, we just are going to do a box plot, right? And doesn't the box plot give me the... We'll find out. Does the box plot give me the sample sizes? It does not. Okay, it does not. Notice we have a couple of outliers, all right? But again, as long as the sample size is greater than 15, the overall sample size is greater than 15, we'll be fine. And since I'm not getting a great way to find the sample sizes, what am I going to do? I'm going to run this. This will help us determine the sample sizes. So we're good here. Okay, and this can go away. All right. So what do we have? Okay, so now we want to run the Anova, right? Okay, and what are we running the Anova on? We're doing the Anova on the same statistical formula that we had in our model, right? The numeric variable, and we have these 3 levels of this category variable, all right? So what am I going to do? I'm going to save the Anova as a variable called Anova, and then I'm going to do AOV Okay, and that's great. I can force it to print if I want to, but I will tell you that summary Anova, the summary view is helpful to us. And what's our p-value to read this right? Degrees of freedom, that is number of groups minus 1. And the total, this degrees of freedom, there's degrees of freedom within and degrees of freedom between. And so 126 is close to the sample size. All right. And the F statistic is 4.34, and the probability, the p-value is 0.0151. Okay, and it even marks the level of significance on the p-value, right, with an asterisk. And if I go down here and find the asterisk, it says, hey, it's significant at the 0.05 level. Okay, so what are we doing? So basically, right, in our reporting out for the Anova, we say we reject the null due to the fact that p equals 0.0151, which is less than 0.05, which equals \alpha. Hence, at least one of these group means is different than the others. Okay? One of these is not like the others. And the reporting out, there we go. What does this mean? Right? This means that, therefore, I will conduct a post hoc Tukey HSD. Okay, why am I going to do that? Well, you'll see that this is very, very helpful. Let me get rid of the straight marks there. So what am I doing? Remember, I saved this as Anova, so I just type in Tukey HSD, but I don't leave a space in here. It's just Tukey HSD in all caps for the Anova. Okay, cha-ching. And the great thing about this is that it gives me all of the pairwise comparisons, and it compares front versus back. And notice the p-value of 0.03. Okay, I look at middle versus back and the p-value here. Okay, so that's not significant, but middle versus front is significant, right? That's 0.05, 0.03. So the top and bottom there are significant. And here's the great thing about Tukey. I can plot them and it will show me the intervals. It will plot these intervals. You notice that we have the lower and upper, right? Those are intervals. And the idea is that they can't include 0, right? If both the lower and upper have the same sign, that means they're all on, the whole interval is on one side of 0 or the other. And so what I want to do is I want to plot Tukey HSD Anova. Just plot it. Oh, and there we go. So this is great. Notice that, right, I have the interval here. It's showing me, and here's 0. So what it's saying is if I subtract the average from the front perfectionism scores minus the back perfectionism scores, 0 is not in the interval, right? Well, the interval is where the difference might be. And if the difference isn't, and if that interval doesn't include 0, that means the difference can't be 0. Well, if the difference is not 0, they're not equal, right? The difference is only 0 when the two groups have the same mean. Now, this interval, you're like, well, the mean could be kind of anywhere in here, you know. Yeah, different places, but it's got to be in this interval, but 0 is in the interval. So we're like, that one is not a significant difference, right? But notice it's barely above, but it is below 0. Both the lower and the upper part of that interval are below 0, so that one's significant. So I see the significance on the bottom, the significance on the top. Okay, and notice it even gives us a nice title, Differences in Mean Levels of SIT Class. Okay, so what does that tell us? Okay. And the best way to write this, you'll see a lot of different people doing it a lot of different ways. Let's just say that our reporting out is that the honestly significant differences are between the front versus back groups and the front versus middle group. That's basically all we're doing, right? Is now we've found the differences and we're telling people what the differences are. All right. Sorry, that needs to switch to a markdown cell. Right. And the honestly significant differences exist between the front versus back group and the front versus middle group. All right. And just for my eyesight, I'm going to put a blank line there. So that's how the whole thing goes, right? Right, we have our hypotheses. By the way, the hypothesis isn't all that different no matter what we're doing. The data verification, again, I look at a density plot of the residuals, a normal QQ plot of the residuals. That's checking all the normality assumptions for all the samples at once. And we're golden here, right? I run the Anova. I do a summary of the Anova, and I get the p-value here. My reporting out is that I do reject the null, and sorry, I need an equal sign here. I do reject the null because p is less than alpha. Therefore, I have to conduct a post hoc Tukey, and I get the confidence intervals for the post hoc Tukey in text, and then I get a visual of them, and I can see where the actual differences between group means exists. Okay. So I'm going to do that again. Optimism scores vary based on primary humor style. Okay, so primary humor style, by the way, look up primary humor style in Wikipedia if you want details. Wait, I'm sorry. What you'll look up is humor style questionnaire in Wikipedia because that's how we determined the primary humor style. And there are 4 of them. There's aggressive humor, that's sarcasm and put downs. There's affiliative humor, which is those are people of the life of the party. They use their humor to bring people together, to put people at ease, right? Then we have self-defeating humor, which is those people who use themselves as the butt of the joke, and they're trying to ingratiate themselves with people, and self-enhancing. This is a lot like coping humor, right? Self-enhancing primary humor style just means that you're the kind of person that when things are going badly, you're trying to make a joke, or you use humor to try to get through the pitfalls of life. Okay, so there are 4 of them. All right, and what are we going to do? Again, they're in the personality data frame, which is already loaded, so we can do mod 2, right, is a linear model. We're doing CHS is our numeric variable. Tilde PHS, primary humor style, is a grouping variable with 4 levels. And the data is in the PERS, the personality data frame. Okay. So we have it loaded. I suppose that what I don't have, right, is the hypothesis. Okay, so we're doing H superscript 0 colon, and now I've got mu sub, and I need to put curly brackets here. Why? Because I'm going to use 2-letter codes. That's for affiliative, sense of humor, primary sense of humor, and then mu sub aggressive, and then we're going to use mu sub SD for self-defeating, and mu sub SE for self-enhancing, and close that, and turn it to Markdown and just make sure that that's looking good. There we go. That's a beautiful null hypothesis. And again, what's the alternative hypothesis? Well, I'm going to start with this, right? And then I'm going to say at least one of the group means is significantly different from the others. All right, so what we're doing here is actually data verification, right? And what do we want to do? What we want to accomplish here is the QQ plot and the density plot of the residuals, right? So let's try this residuals this way again. This was working before, and I don't know exactly why it didn't. All right, so residuals mod 2, and I'm going to call that res. Okay, and then what am I going to do? As always, do the layout, the matrix, the concatenate function with just a 1, 2. I'm going to do the endcall equals 2. All right, and then what? I'm going to plot a density plot of the res, and let's just see if it works. Yeah, it's working. Okay, excellent. And then I want to do plot 2, and I want to use these curly brackets to put two things in, right? I want to do QQ norm of the res. Right, and I want to do the QQ line of the res. Let's see if that's going to behave. There we go. Perfect. All right, so this is the one I prefer. Can we do it with some dollar signs and mod $sign residuals? Yes. I like this better for Anova. And notice that we don't have any problems to the north end on our QQ plot. There's a slightly heavy tail down here. But these don't stray too far, right? We do have a slightly heavier tail over to the left. Things look normal to the right, okay? So this is fine. I mean, we're going to note it, right? But we're not going to freak out. This is going to be okay. So data verification results, right? These data are appropriate for Anova procedures, right? The QQ plot has a heavy tail to the left, but the deviation from the line is not too great, or is not too much, right? We're admitting, okay, the density plot appears normal. We must be careful as accuracy may be slightly, and I mean very, 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 very slightly compromised. But the data are okay for Anova procedures, and you know, we're going to go with this, right? This is going to be fine. All right, so what I'm going to do is I'm going to call this Anova 2. And what am I doing? The function is AOV. I'm doing the same linear model from up here, right? It's the CHS, the coping humor, versus the primary humor style. The data set is the same. So I'm doing the analysis of variance of that model. And then I'm looking at the summary of Anova 2. Right? So what do I have? I have a p-value that's switch to scientific notation. So 8.74 times 10 to the negative fifth. Wow, so we reject the null, right? So this one was easy. And so what do we get when we do our reporting out? And we're going to say we reject the null due to the fact that P is equal to, and again, 10 to the negative fifth, that means the first non-zero entry is 5 decimal places to the right. Okay, so that's going to be 0.12340 zeros and then the 874. And that is clearly less than 0.05, right, which is our alpha. We have evidence that at least one group mean is significantly different from the others. Excellent. Okay, thus we will conduct a post hoc Tukey HSD. You can call it test. Maybe analysis is a better word. Let me also throw in some italics around post hoc. It is Latin, so it's actually correct to italicize a foreign language, right? So then the post hoc Tukey HSD, right, is real simple. We've run the Anova, so all the code is, right, is I just do Tukey HSD. Sorry, I missed this. Tukey HSD, then do the parentheses and Anova 2. And now we've got more groups, right? So we have more of these. And notice where we get a p-value that's smaller, okay, but not less than 0.05. The bottom two are less than 0.05. And notice that the lower and the upper are both positive. So that interval is above the zero line. These are both positive, so that one is also above the zero line. All these others, the endpoints of the interval, have different signs, which means that they include zero, right? Which is what we're trying to avoid. Okay, so we just have 2 here. Again, I am going to plot these, and that's why I copy-pasted, because I just want to plot the exact same thing that I ran. And you can see everything includes 0 inside the interval, barely inside the interval, but inside the interval. And here we go. Here are the two pairs of groups that have an honestly significant difference. So SE versus AG and SE versus SD. Okay, so I'm going to keep that just in line, in sight, while I do this reporting out again. So the final reporting out is that we have, we find honestly significant differences between the SE and SD groups and the SE and AG groups. Okay, and then no other honestly significant differences exist. Some people do write that out. I'm not going to. I report the ones that are there, and I don't spend a ton of time reporting the ones that are not. Again, a lot of times we give them either a graph of the confidence intervals, or we give them the Tukey HSD table so they can see, the numbers, but we just are going to report on the ones that are significant. Okay, now cities and populations. All right, so what I did here is I subset the data frame, so it's a data frame called data. And I did head data just so you can see that we have this huge data set with nearly 200 different countries. But what they do is they list all of the large cities in the countries. All right. And so here, what I want to do And the hypothesis is the same as it's been over and over. So I might actually go copy paste it. Let me make this a markdown cell. And done this hypothesis thing several times. Oops, Control Z, I want to be in here. And so here we have China, Brazil, India, and Japan. Those all start with a different letter. So I'll do mu sub C, mu sub B for Brazil, mu sub J for Japan, and mu sub I for India. And so what we're doing is we have all these large cities, but the question is, are the cities larger in Japan than they are in Brazil? Are they larger in China than they are in India? Or are they larger in India than they are in Brazil? And the answer is we don't know. That's why we're running the test. Okay. And data verification. What are we doing here? Right? We're going to do our model. And I've done this before. I just don't like using the same variable names. That's why I'm using mod 3, right? A linear model of what? Well, in the data frame, what are the variables I have? I have population, and I want to sort out by country, not city, but country. Okay? So my numeric variable is going to be population tilde country, and the data equals city. I think that's the name of this. I have to look back at where we pulled it in. That's miles away, but there it is, city. Since that's the name of my variable, right, this will work as long, I mean, this is the name of my data frame, so this will work, right? And then I want to do the residuals of the Model 3. Okay. And what do I want to do? Oh, yeah, I wanted to name that, so I don't want it to print out. Let me call this res3. There we go. So we created the model, created the residuals, and then we're going to do our layout and our matrix and our concatenate 1, 2, and our comma and call equals 2. All right, so that gets us the grid that we need, right? And we're going to plot the density of res3, right? And the main title will have be density residuals. Okay, and then we're going to do plot 3 and put in our curly brackets, right? And what is that? What is it that we need to do? We're doing QQ norm of the res3, and we're doing the QQ line of the res3. Okay, and this should do everything that we need to. I was going to put a title in, but let's save that for a moment. It just says normal QQ plot. Let's see if it'll change. At times, some of these plots don't allow a name change, but we can do QQ plot of the residuals. And it did it fine. But OMG, like, look at this. This is an absolute nightmare. It's supposed to be linear and it's more like a parabola. I mean, not over here, but still, this is a massively heavy tail, right? And then this departure, no, this just crashed, right? Is there an approximate bell shape? Well, there's this spike. I'm not sure that you would call it a bell. It's so tall and narrow. Right. So we have a phenomenally busted model, right? What's our result going to be? So our data verification results is these data are not appropriate for Anova procedures. I mean, it was an interesting question, but we're not going to be able to answer it, right? This data verification just failed massively. I mean, massively. Um, so what I try to do on the quiz and on the final project and stuff, when you get one of these where you are supposed to fail the data verification, again, I try to make it really clear, like, oh, ginormous deviation from the linear. Yes, definitely doesn't work. So I try not to leave you in that gray area. I try to give you a density plot or a QQ plot that's really pretty close. There might be a couple tiny anomalies, but it's going to be pretty close. And then when I need you to reject the verification and say no, these data are not appropriate, I want to make it something massive, right? So that'll be clear. So we try not to leave you in that gray area, and we try to do that as often as we can. We try to not leave you in the gray area as often as we can. Um, so that you do have a way to earn the points that you deserve for your understanding. So that's ANOVA, and that also concludes the information that's going to be in this course. Thanks for following along in all these videos. It was my pleasure, and good luck on your final project.